So what happens if you're doing a chemical reaction and one of your reactants is not in excess, is not as much as you need? What if you have to figure out which reactant is going to control the reaction? That's what we're talking about today in limiting reactant. I want to talk about s'mores. Why? Because I like s'mores. We're going to talk a little bit about s'mores as a model for understanding this idea of limiting reactant. It's a very simple concept, and it makes more sense if you think of something yummy and delicious like s'mores. Okay? You could think of s'mores as being part of a reaction to produce a s'more. So you need some graham crackers, and you need some marshmallows, and you need some chocolate, and you put them together with some heat, and you get yummy deliciousness. Now, all of those things by themselves are pretty cool. Put them together in a s'more, and it's downright amazing. Right? Let's be a little bit more specific, though. My recipe for s'mores is 2 graham crackers, top and bottom, right? 1 marshmallow, a nice big marshmallow, 3 chocolate pieces, or pips. That's what they're called, by the way. Did you know that? The little rectangles on a Hershey bar are called pips. And that equals 1 s'more. So that's my recipe, right? So in order to do that, I need 2 graham crackers, a marshmallow, 3 of these chocolate pips, and that'll get me 1 s'more when I melt it on the heat. So I want to make some s'mores. So I need to go into my kitchen and I need to gather together the materials, the ingredients, to make my s'mores. And I go into the kitchen and I find a big bag of Jet Puffed marshmallows. You should never use any other kind of marshmallows but Jet Puffed. A box full of graham crackers and about 4 Hershey's chocolate pips. Probably one of my kids ate the other ones. I know there were more in there. A whole box of Hershey bars, and now there's only 4 little pieces left. Who leaves 4 pieces of chocolate lying around? I mean, honestly, put them in a bag or something. That's disgusting. Anyway, I've got a problem now. I have a lot of marshmallows and a lot of graham crackers, but I don't have very much chocolate. And according to my recipe for s'mores, I can't make very many s'mores. As a matter of fact, looks like I can make 1. And then have a little piece of chocolate left over, or I can make an exceptionally chocolatey s'more. But I'm not going to get much more than 1 out of this. I'm limited because one of my ingredients, I just don't have enough of it. And that's what we mean by limiting reactant, okay? One of the reactants in a reaction is not going to be present in a sufficient amount. And that means that that reaction is going to get used up before the other ones. Well, when the reactant gets used up and it's gone, that means the reaction is going to stop. So that reactant, that ingredient, limits the amount of product that I can make, because once it's gone, I won't make any more product. That's what we mean by limiting reactant. Okay? Now, to find the limiting reactant is fairly straightforward. Okay? First of all, you have to know whether or not you need to do it. And the key is, if you're reading a problem and the problem gives you information about both reactants, that's a clue that you're going to need to figure out which one of those is the one that's going to get used up first, because that's the one that's going to determine how much product you can make. Okay? You essentially need to answer this question. If I start with the given amount of one reactant, how much of the other reactant do I actually need to react it all away? And then you can calculate that amount, and then you can compare it to what you have. And if you have more than you need, then you know that's not the reactant that's going to get used up. And if you don't have enough, then that is the reactant that's going to get used up. Might make more sense if we do an example. Okay, so here's an example. I have 2.5 moles of lithium metal, and I'm combining that with 1.75 moles of oxygen gas. Now, I've got information about both of my reactants there, so that's the clue that I'm going to need to know what my limiting reactant is. Okay, I want to know which one's going to get used up first. In other words, which is the limiting reactant. So I'm going to start with a balanced equation, because this is nothing more than stoichiometry. So I need a balanced equation between lithium metal and oxygen gas to form lithium oxide. So let's get a balanced equation. There it is. 4Li plus O2 goes to 2Li2O. Mole ratio between reactants is 4 to 1. I need 4 times as many moles of lithium as I have of oxygen in order for this to work. Okay, very simple calculation to do. The question I'm going to ask myself is this. If I start with 2.5 moles of lithium, how many moles of oxygen do I actually need? All right, so it's just a simple one-step mole ratio calculation. Okay, 2.5 moles of lithium. The mole ratio is 1 mole of oxygen to 4 moles of lithium. Remember, moles of what I have goes on the bottom. Moles of what I'm looking for goes on the top. That's 0.625 moles of oxygen that I need. Okay, now I compare. So I need 0.625 moles of O2. but I have 1.75 moles of O2. I have more than I need. And since I have more than I need of the oxygen, that means that I'm not going to use it all. I'm only going to use 0.625 moles of it, and all of the lithium is going to get used up in that process. So the lithium is going to get used up first. That means the lithium is the limiting reactant. Okay? That's how you figure out which your limiting reactant is. How about this? I've got 0.750 moles of liquid butane, C4H10, and I'm combusting it, combustion, with 1.07 moles of oxygen. Which reactant is the limiting reactant? Which one gets used up first? All right, so again, I need to start with a balanced equation. Here's my balanced equation for this reaction. 2 butane, 13 moles of oxygen, 8 moles of CO2, and 10 moles of H2O. Larger numbers, but it doesn't matter. I treat it the same way. Okay, so the question I'm going to ask myself is, if I start with 0.750 moles of butane, how many moles of oxygen do I need? I need 6.5 times the number of moles of oxygen as the moles of butane, right? Because it's 2 to 13. So do the calculation. 0.750 moles of butane, 13 moles of O2 to 2 moles of C4H10. That gives me 4.88 moles of oxygen that I need in order to react all of my methane away. Okay, so let's compare. I need 4.88 moles of oxygen, but I don't have that. I only have 1.75 moles of oxygen. So in order to react all of my butane away, I have to have more oxygen than I actually have. I don't have enough. And since I don't have enough, that means the oxygen is going to get used up first. That means that oxygen is the limiting reactant. Okay? So why do we do this? Well, if you remember, the point of stoichiometry most of the time is to predict amounts of substances without actually doing an experiment. Well, the reactant that gets used up first is the one that we need to start with, okay? Because the reaction stops when that one's gone. So once I know the limiting reactant, I can do some calculations, but I have to start with the limiting reactant because I won't make any more product once that limiting reactant is gone. Okay, so always start with the limiting reactant. That's why you have to know. Now, sometimes, here's the opposite of the clue that I told you before. The clue that you're going to need to find the limiting reactant is if you have information about both reactants. If you see the word "an excess" of something in the description of the reaction, that means you don't have to worry about the limiting reactant, because excess means you have more than you need. You're going to have some left over. So whatever thing is excess is not the limiting reactant. The other one is. But sometimes you have to figure it out. Okay, so here's a real type example. I'm going to start with a gram of iron metal, and I'm going to react it with 3.50 grams, 3.5 grams of copper 2 chloride in solution. And I want to know how much copper is going to form when I do this. All right, well, I've just sort of, spoiler alert there, I know copper is one of my products. Well, hopefully you were able to figure out, hey, this is a single displacement reaction. So I'm going to get copper and iron 3 chloride, okay? So let's start with the balanced equation. After that, we're going to determine which is the limiting reactant. How do I know I need to do that? Because I have information about both reactants. I have to figure out which one gets used up first. Then I'm going to start with that limiting reactant and calculate the mass of product. All right, so there's my balanced equation. 2Fe plus 3CuCl2 goes to 2FeCl3 plus 3Cu. Figure out which of my reactants is the limiting reactant. I say, okay, well, if I use up a gram of iron, how much copper chloride do I actually need? Now I'm working in grams, so I have to go a little further. I have to first go to moles of iron, molar mass. Then I use the mole ratio, moles of copper chloride, the other reactant, to moles of iron, 3 to 2. And then I convert that to grams of copper chloride, the other reactant, 134.45. And according to this calculation, it tells me that in order to react a whole gram of iron, 1 gram of iron, I need 3.61 grams of copper chloride. Well, do I have that? No. I've only got 3.50 grams. I don't have enough copper 2 chloride to react all the iron away. The copper chloride is going to go first. There's going to be leftover iron. So copper 2 chloride is the limiting reactant. That's what I have to start with now to find out the mass of copper. Okay? So I start with the mass of the limiting reactant, which was CuCl2, and according to my problem, I only have 3.50 grams of it. I convert that to moles using the molar mass. I use the mole ratio from the balanced equation, moles of copper to moles of CuCl2. It happens to be 3 to 3 or 1 to 1. And finally, I want the mass of copper, so I need copper's molar mass. Turns out that I'm going to be able to make 1.65 grams of copper from this reaction. I will have some leftover iron in there, but that's the maximum amount of copper that I'm going to be able to make. Okay, so finding the limiting reactant, fairly simple. Sometimes you have to do a little bit more to get it to moles and then convert from moles to moles of the other reactant and then convert to mass of the other reactant like we did in this one. But essentially the calculation is pretty much the same. Start with the mass or amount of one reactant, figure out how much of the other reactant you have to have, and then compare to what you actually have. If you don't have enough, that's the limiting reactant. If you have more than you need, the other one is the limiting reactant. Pretty straightforward, but we do it all the time.